physicists derived the ideal gas law and saw the relationship between the pressure of a system, the volume of that system, the amount of gas in that system, how many molecules you've placed in that closed container, and the temperature. But what really is going on in that ideal gas law? And to figure that out, you have to come up with an idea called the kinetic theory of gases. Now, the kinetic theory of gases, again, is the assumption that gases are little tiny billiard balls bouncing around, moving freely from one another, only interacting with one another when they collide with each other or with the walls of the container. That's it, right? Elastic collisions with the walls of the container or elastic collisions with one another. So the pressure, so we have a little cross-section of a wall. Imagine that this is a square container. I'm looking at the inside wall here. The rest of the container is enclosed. What causes pressure, right? Think of this as, or a small little cross-section of a balloon. What keeps the balloon up? Why doesn't the balloon shrink, right? It's rubber, it wants to stretch down. Why does it inflate when we add more air or increase the temperature? Well, the reason it inflates is due to pressure of the gas from the inside of the balloon. Well, what causes that pressure? Physically, what is pressure? Well, an air molecule, or say a helium balloon, a helium atom, crashes, moves with some velocity, hits the side of the wall, and bounces off. Again, these are elastic collisions. So if this is the wall of the balloon here, I'm the helium molecule, I come, hit it, and bounce off. That change in momentum, right? The helium atom has some momentum in the upwards direction, hits, moves back. There's a change in momentum there. That change in momentum is caused by an impulse, right? That's an impulse. That impulse is caused by a force. So what happens is the reason that this is accelerated is the wall is applying a force to the molecule, changing its velocity, giving it an acceleration. And likewise, according to Newton's third law, the molecular atom here is applying a force on the wall. That force is pushing the balloon up. Now, this has some area associated with it, right? So we have a pressure. Force divided by area is pressure. So the pressure is caused by the force of the collisions from the molecules inside the balloon, inside any container. Now, so we have a physical definition for what pressure is. Volume, again, we know physically what volume is. It's just how big is the inside of the container. Not as surprising. Physically, we know what N is. N is capital N here is just the number of molecules we have in there. We have a physical understanding of what that means. This is just a constant that allows us to convert between the units we selected. So what is T, temperature? Temperature is still kind of a vague, out there concept. So let's try to physically come up with a reason temperature exists. When you take the temperature of something, what are you physically doing? What does the temperature actually say? What physical thing is it connected to? Well, we know in the ideal gas law, again, this equation, all things being equal, if you decrease the volume, you increase the pressure. So if you can physically crush down a balloon, you increase the pressure in that balloon, all other things being equal. All other things being equal, if you increase the number of molecules in the volume, you increase the pressure. That's how bike tires work, right? You push more and more molecules in there, increasing the pressure. And if you increase the temperature, you increase the pressure. There's a linear dependence there. So the temperature goes up, the pressure goes up. Again, what is the physical meaning of T? Now, your book goes through a very long multi-page derivation to get to the equation that I'm talking about. Look over that derivation. You should be able to follow logically and algebraically what is going on. And it gives you some intuitive feel for how physics is done. Now, this is a Physics 141 course. I'm not going to have you recreate that derivation, nor am I going to bore you with a 15-minute lecture just going through the same derivation, maybe using a slightly different method on the board, because you have it in your book. But what is the end result? What is temperature? Well, your book comes up with this equation here. V RMS, that's the root mean square velocity. Root mean square is the root of the mean of the square of a number. think of this as a type of average. So this is an average speed. Now, if you think about in a room like the one we have here, if these molecules are really like little billiard balls bouncing off one another, then sometimes when two hit, they stop and stay together until another one comes by and smashes the stationary molecule. So the speeds of the air in this room vary greatly. Some molecules are traveling very quickly, some are traveling very slowly, but they have to have some kind of an average speed. Well, the root mean square speed here you can think of as an average speed. The average speed of molecules in a room or in a container is equal to the square root of 3 times Boltzmann's constant, again that's just a constant, times the temperature in Kelvin over the mass of the object. So low mass molecules like helium will have a greater RMS speed at a given temperature than fat, heavy xenon will, than massive xenon will at the same temperature. But what this shows is that a temperature is related to the speed of the atoms in a room. Massive molecules will be traveling slow, low mass will be traveling very quickly, but temperature is a value related to the speed. There's mass in here as well, though, and mass is independent of temperature. What you can do is rearrange this equation, square both sides, multiply both sides by m, divide both sides by 2, and you can rearrange it to kinetic energy on one side of the equation. So the average kinetic energy of a molecule or an atom in a gas is equal to 3/2 Boltzmann's constant times temperature. This is a pretty awesome equation as a result of this kinetic theory of gases. What this states is that a temperature is just the measure of the average kinetic energy of the molecules in an object. So when you take your temperature, right, you put your thermometer, different types of thermometers, you have the mercury thermometers, alcohol thermometers, the new infrared camera thermometers, swipe your forehead or stick a camera in your ear and take a picture type thing, looking at the infrared radiation. That is a measure of how quickly the atoms in your body are moving about, what the average kinetic energy is. So temperature is related to the speed of the molecules, because speed, of course, is part of the kinetic energy. Kinetic energy has mass and speed in it. So hopefully now you can see from a physical standpoint why when the temperature increases, the pressure increases. When the temperature increases, the speed of these little molecules increases. They hit harder. And since they hit harder, they give more force to the walls. As n increases, you just get more hits, right? As you increase n, the pressure goes up because you have more molecules hitting. Double the number of molecules, you double the pressure because you double the number of impacts. Temperature, on the other hand, is related to the kinetic energy. So as the temperature goes up, the kinetic energy of these particles goes up, smashing into the wall, transmitting more force, more energy basically to hold those walls up. So temperature is related to the average kinetic energy of molecules. Now this holds strictly for monatomic gases. So gases like helium or xenon or krypton, where they're just a single atom. When you start getting molecules, at low temperature this holds, at high temperature this can break down. But for right now, we'll stick with this equation. So temperature is just a measure of the average kinetic energy. Now when the temperature goes to 0, Kelvin, remember, always Kelvin when it's just a temperature. When the temperature goes to 0, the speed goes to 0. This gives us the classical idea that in a room where you could turn the temperature to absolute 0, the atoms and molecules would just fall to the floor, right? They would not be moving at all. They'd have 0 velocity. They wouldn't just hang there in the air with 0 velocity because gravity's still pulling down. Right? So these things would just fall and lay on the ground. The atmosphere would freeze out of a room. So this is all due to the kinetic theory of gases. And again, this theory works really well in explaining why the ideal gas law works, There are some couple of small changes you need to make to it at the extremes, very high temperature, very low temperature, very high pressure, and so on, because of interactions between the molecules, other small forces. But for a monatomic ideal gas that's not charged, right? These are like helium. Helium is really a wonderful ideal gas. The ideal gas law holds, and these relationships all hold.